Hello, IB physicists. So today we are going to talk about how we can understand circular motion quantitatively. So we know that for an object to move in a circle, it needs to have a net force towards the center of the circle. And so we're going to figure out how we can do some equations for calculating how much force is required for that object to move in a circle. And we're actually going to start out with using some vectors. Excellent. And so here you see in this diagram we have an initial velocity, and notice that the velocity is tangent to the circle. So you can see that the initial velocity is here, we have our final velocity here, and we're going to go ahead and calculate the acceleration on this circle. And you know that acceleration is the change in velocity divided by the time. So first, we're going to really think about, well, what is the change in velocity? And here, it's an especially tricky calculation because you notice that these two vectors, the initial velocity and the final velocity, are actually pointed in different directions, which is kind of weird. And that's because the direction of the velocity is constantly changing as an object goes in a circle. And so we can do a little bit of graphical subtraction here. So I have the final velocity, and notice that I've taken the initial velocity and I've drawn the opposite of it since I'm subtracting the initial velocity. And you can see that these two vectors together, the resultant or change in velocity points towards the center of the circle. And in fact, this is true all the time. When an object is moving in a circle, its change in velocity always points towards the center of the circle. And you can do some more derivation with this if you're really jazzed about doing some more math, but we're going to notice this visually and be like, interesting. So this change in velocity is pointing towards the center of the circle. That means the direction of the acceleration, in this case, the centripetal acceleration, which means center seeking, the center-seeking acceleration is towards the center of the circle. And this probably makes sense to you because you're like, Ms. Getz, I know the net force, that's supposed to point towards the center of the circle, and a net force equals mass times acceleration, so that should track up that the acceleration should be the same direction as the net force. And in fact, we can then do some more math to derive an equation for this centripetal acceleration from this circle relationship. And I have a link to a derivation video if you're really excited to see how that derivation works geometrically. But I'm just going to hand you this equation because you don't need to derive it. You're going to have it available to you in your equation booklet and on your note card. So we get this equation for the acceleration of an object moving in a circle, the centripetal acceleration. And that is equal to the velocity of that object squared divided by the radius of the circle. And so from this really useful equation, we can actually note that there are some differences between this centripetal acceleration and linear acceleration. So first, centripetal acceleration is perpendicular to the velocity. That means that if I go back to my picture here, the acceleration is actually going to be pointing inwards to the center of the circle, which at either of these points inwards to the center of the circle is at a right angle relative to the velocity vector. So centripetal acceleration is perpendicular to velocity, whereas a linear acceleration, like we've used for a long time, is parallel to the velocity. Either it's speeding the object up or slowing the object down, but it's parallel, either the same direction as velocity or opposite direction for a linear acceleration. Centripetal acceleration also causes a change in the direction of the velocity. And so here our velocity is a velocity that technically we're really talking about a speed. We're not talking about the direction of velocity, it's tangent to the circle, but here technically we're really talking about a speed. Whereas a linear acceleration changes the magnitude of the velocity. It either slows down the object or speeds up the object, depending on the direction relationship between that linear acceleration and that linear velocity. And so the consequence of this is the final big difference is that centripetal acceleration changes its direction. The acceleration is changing direction constantly as you move around a circle. Its direction is changing. And that means we actually can't use our Suvat equations at all. We can't use these Suvat equations at all because they only are valid when the acceleration is constant. That would mean that it's a constant value and a constant direction. And in our case here, when we're moving in a circle, the centripetal acceleration is a constant value, but it's not a constant direction. And so we can't use our Suvat equations, so we have to use just this acceleration equation that relates the velocity of the object moving in a circle, that's circular velocity, and the radius of the circle. So when we have something that's in linear motion, it's accelerating because it's falling, or it is a car driving on a road in a straight line, we can use our Suvat equations, but here in circular motion, not so much. So the key here, though, is that we're still talking about the same acceleration, the same idea that we have a change in velocity. Because here, while we're moving in a circle, the thing that's changing about the velocity is its direction, which is kind of nutty, but kind of cool. And so that means that we can still use Newton's second law, that the net force is equal to the mass times the acceleration. And that means that we can calculate lots of different forces on objects when they're traveling in circles. So I'd like you to pause right now and start working on setting up this problem using that same free body diagram that you drew in your qualitative practice from workshop 2 to help set yourself up for doing some calculations for some different forces here in this problem. So please pause the video now and then unpause when you've tried starting this problem. All right, so let's go ahead and think about what's happening in this problem. We're looking at this boy who's upside down here on this roto ride. And so the forces acting on him are going to be very familiar to you since they're the same forces you set up in our problem set earlier from workshop 2. We have force gravity pulling him down. The thing that's actually balancing out force gravity is force friction, the friction between the surface and the boy. And then the thing that's allowing him to continue moving in that circle is that the circle itself is this little wooden circular ride, and the wall of the ride is pushing on him inwards towards the center of the circle with a normal force. And so here we can set up some knowns that we know from the problem and consider the forces and how they relate to each other. So what we know from the problem is that the mass of the boy is 55 kilograms. We know the boy is traveling in a circle that has a radius of 10 meters. And that his tangential velocity or tangential speed is 17 meters per second. And so we're going to try to determine the direction and magnitude of each force on the boy. And so we can start out with that force that's generally, I think, a pretty useful starting place, and that is force gravity. But before I do that, I'm going to set up a little sum of the forces table just to help me keep track of what's happening. So I've got two different directions here. I've got the up-down direction, and so I'm going to call that the y direction. So in the y direction, what forces do I have? Forces in the y direction. Well, we have the force of friction upwards on the boy and the force of gravity downwards on the boy. And those are going to add together to equal 0 because the boy isn't falling down or sliding up. So I can actually say that these forces are going to be equal in magnitude. And then in the direction that's along the radius of the circle, I'm going to call that the x direction, or you could call it the radial direction. We have this normal force from the wall. And this normal force from the wall is the force that's allowing the boy to move in a circle. So we know that it actually is going to add up to the net force that is causing him to move in a circle. Cool. Out the force of gravity on the boy. I know force of gravity equals the mass times the acceleration due to gravity. And so that is 55 kilograms multiplied by 9.8 meters per second squared. I think if you want to get the exact answer I gave you, you might have to use 9.81 meters per second squared. And oh no, oh good, okay. And you do in fact get 539. Great. Okay. So we get 539 newtons. And we happen to know that that actually is going to be equal to that force of friction as well, 539 newtons. And I want to say the direction. So it's asking for both the magnitude and direction of each force acting on the boy. So force gravity is down and force friction is up. So I'm giving really simple directions. So then finally, to be able to find this normal force here, I'm going to use my centripetal acceleration equation to say, oh, I know that the net force, Newton's second law tells me the net force is equal to the mass times the acceleration. In this case, it's a centripetal acceleration because we're moving in a circle. So that'll be the mass times the velocity squared divided by the radius. And we also know that that net force, well, that's equal to that force normal that we're looking for. So what I've just done is made myself an equation to calculate this normal force on the boy. And it just so happens that it's exactly equal to that net force. And so I can write down, I need the mass of the boy, that's 55 kilograms, multiplied by his velocity squared, 17 meters per second squared, and divided by those 10 meters. And so I can plug that in on my calculator again. 55 times 17, don't forget to square the 17. And I get 1,589.5. And you might go, Ms. Katz, what do the units work out to here? And so you can check in with that and say, I've got meters squared over seconds squared. There's a meters on the bottom. So the units actually end up being kilograms times meters divided by seconds squared, which is in fact the exact units for newtons. And we want to add in what direction that force is, and that's towards the center of the circle, if you had room to add that in. So hopefully this was helpful for you. You're going to keep on working on solving these quantitative circular motion problems and really go through this process of setting up that free body diagram. Use the practice free body diagrams we did for workshop 2 to help you. Think about the net force and the sum of the forces in all directions. And then use your equation for centripetal acceleration and Newton's second law to help you do some calculations for these net forces. You got this, guys. Good luck. Oh, and I made it under time. Woohoo!